In this lecture, we will study Fourier transform and its application in physics. We are already familiar with Fourier series analysis. However, we have given a very short introduction to it. Any single valued function fx defined on the interval minus pi to pi may be represented by in this interval as a trigonometric series fx equals to a naught divided by 2 plus sum over n equals to 1 to infinity an cosine of nx plus bn sine of nx, where expansion coefficients an and bn are determined as an equals to 1 over pi minus pi to pi integration fx cosine of nx dx, where n goes from 0 to infinity, and bn 1 over pi minus pi to pi fx sine of nx dx, where n goes from 1 to infinity. Expansion is restricted to minus pi to plus pi, but in many physical situations it is necessary to develop Fourier series that will be valid for a wide range of interval, say minus L to plus L. Let us consider the Fourier series fx equals to a naught by 2 plus sum over n equals to 1 to infinity a n cosine of alpha x and b subscript n sine of alpha x. We have to determine alpha such that fx equals to fx plus 12. That's imply alpha equals to n pi by L basically. Therefore, the Fourier series becomes fx equals to this. And this is basically valid for minus L to plus L, and the function must satisfy the Dirichlet's condition as you already know it. Bn also written as 1 by L minus L to plus L fx cosine of n pi x by L dx, where n goes from 0 to infinity, and Bn 1 by L minus L to L fx sine of n pi x by L dx, n goes from 1 to infinity. Therefore, we have fx equals to 1 by 2L minus L to plus L, some variable t ft dt, and 1 by L sum over this as written here ft, the first bracket cos n pi x by L cosine of n pi t by L sine n pi x by L and cosine n pi t by L, and integrate over dt. And we simplify this expression, trigonometric expression, and we'll get this thing fx equals to 1 by 2L minus L to L ft dt 1 by L sum over n equals to 1 to infinity, and integration over minus L to plus L ft cosine of n pi L x minus t dt. Now we let some variable xi that is equals to n pi by L, where 1 by L equals to delta xi by pi, since delta 1 equals to 1. And therefore, if we substitute this in our expression, we will get fx equals to 1 by L minus L to L ft dt 1 over pi, and xi goes from pi by L to infinity delta xi and minus L to plus L ft cosine of this thing, integration over dt. To find out that expression in the limit as L tends to infinity. So therefore, the first term 1 by 2L ft dt, which goes from minus L to L, must be 0, and that delta xi becomes d xi, and where xi is where the integration limit goes from 0 to infinity. So therefore the above expression can be fx can be written as 1 by pi integration 0 to infinity d xi and minus infinity to plus infinity integration ft cosine n pi by l into bracket x minus t bracket close third bracket close and dt. This is called the Fourier integral formula. Now we turn our expression into a complex form. Fx already know that expression, and if we convert it into by Euler's formula, as we are familiar with, which is a very useful formula, e to the power I theta is equals to cosine of theta plus I sine theta. And if you put in that form, and that the Fourier series can be written in terms of this complex number, that is fx equals to n equals to minus infinity to plus infinity some coefficient cn e to the power I pi nx by l, where the coefficient can be written as cn, that is equals to 1 by 2l minus l to l fx e to the power minus I pi nx by l. Here also the periodicity is from minus l to plus l. Till now we have studied only the periodic function. Right now our aim is to extend the periodicity factor L goes to infinity. So therefore we say let us consider k equals to n pi by L and take delta k, that is delta n pi by L. Since delta n is 1, so therefore we can write delta k by pi times L, that is equals to 1. If we multiply the complex form of the Fourier series of the each term by L pi by delta k, then the Fourier expansion can be written as sum over CLK e to the power ikx delta k, where n goes from kl by pi, which is nothing but minus infinity to plus infinity. The index is kl by pi, which is infinity, where the coefficient can be written as CLK, that is 1 by 2 pi minus L to L fx e to the power ikx dx, where the new coefficient CL, which is a function of k, LCN by pi. In this limit L tends to infinity, which can be written as ck 1 over 2 pi minus infinity to plus infinity fx e to the power ikx dx, whereas fx is minus infinity to plus infinity ck e to the power ikx dk. Is written in a very precise manner, where fk equals to 1 over 2 pi root 2 pi, that is equals to minus infinity plus infinity fk to the power ik x dx, or whereas fx is 1 over root 2 pi minus infinity plus infinity f function of k e to the power ikx dk. This is a Fourier transform pair. This is called Fourier transform pair, where 2 pi is distributed in the two terms. Here is 1 over 2 pi, and then in other is 1 over 2 pi. And in different books, in different notations, they are somewhere in the fk expression this is 1 and here is 1 over 2 pi and something is there. Many choices are there in different books. It follows different choices, but here fx should be integrable in some finite region. In practical sense, it might have some discontinuities, jump discontinuities or mild infinite discontinuities, but fx must be 0 as x tends to plus minus infinity, and sum over minus infinity to plus infinity, the mod of fx dx should be the convergent finite one.